30. Infinity, Infinities and Hilbert's Hotel. 1. We encounter some marvelous seasonally festive day, traveling maids a-milking and lovely lords a-leaping. I bet there's the same number of maids as there are lords, announce I, ignorant of traditional numbers in such festive matters. I bet not, responds my traveling companion. Bet's taken, we could count the maids and lords, but my companion points out that we can, instead, pair off the maids and lords. If one maid or one lord or more are left over, unpaired, we know that the maids and lords differ in number. The task, easy to do in theory, is not so easy in practice, in view of the leapings and milkings, but eventually we manage, and, sure enough, I lose. We find that some lords are left a-leaping, unpaired with maids a-milking. Clearly, there are more lords than maids. That should be the tale's end, except my companion, an itinerant mathematician, is bearing a gleeful smile, aware of my lack of mathematical skill. Of course, smiles she, if you have a group of items and then take some away, you are left with fewer items than the original number. I readily agree, even I can see that. She now directs me to the whole numbers 1, 2, 3, 4, 5 and so on, and then starts to remove the odd numbers. I casually remark that the remaining even numbers, 2, 4, 6, 8 and so on, would be fewer in number than the original set of 1, 2, 3, 4, 5. The means, and so on, without end. Caught you, her mirth magnified way beyond justification. Look, she says, you can pair off all the original numbers both even and odd, with just the even numbers, without end. The natural numbers, 1, 2, 3, 4, the even numbers only, 2, 4, 6, 8, and so on, and so on. Paradoxically, there are as many even numbers as there are even and odd numbers together. If both groups, maids and lords, were each infinite in number, there would yet be as many maids as both maids and lords. I see the point. Although the set of even numbers contains just some of the even and odd numbers, the set of even numbers is the same size as that of the even and odd numbers combined. My companion has shown this by pairing off, matching, corresponding. She tells me that two infinite sets are equinumerous, equal in number, if there is at least some order such that the two sets can be paired off with each other, without remainder. On that understanding, the squares of numbers, namely, 1, 4, 9, 16, and the cubes of numbers, namely, 1, 8, 27, 64, are also equinumerous with the positive whole numbers 1, 2, 3, 4, as are many, many more series. All very interesting, yawn I, but then infinity is endless, so these series are bound to match. You can't have anything bigger than infinity. My companion's smirk shows that to be a faux pas, a faulty step indeed. Some infinities are bigger than others, she announces. And I am left wondering, can anything be bigger than infinity? The question is whether some number of items exceeds an infinite number. The quick answer is, yes. This was demonstrated by the great mathematician Georg Cantor, who developed transfinite mathematics, dealing with differently sized infinities. Pairing off the items of certain sets and series with the infinite series of whole numbers, 1, 2, 3, 4, 5, still leaves some items remaining unpaired. Let us focus, for example, on the decimal numbers, the real numbers, between 0 and 1. They are infinite in number. There are, of course, the decimals that derive from the fractions 1/2, 1/4, 1/8, represented as 0.5, 0.25, 0.125. There is an infinite number of them. There are also fractions such as 1/3, 1/6, represented as recurring decimals 0.333, and 0.16666. These latter two examples clearly have decimals that are endless. There are others, for example, one that derives from the square root of 2, with 1 deducted. This cannot be represented as a fraction, it is an endless decimal, 0.4141. Now, pop this infinite number of numbers, in whatever order you like, and pair them with the natural numbers, 1, 2, 3, 4. Here is an arbitrary scattering, with highlighting yet to be explained. The natural numbers, 1, 2, 3, the decimal numbers, 0.3333, 0.1428, 0.1250, 4, 0.4141. The infinite series of decimal numbers goes down the page without end, and is paired with the infinite series of natural numbers. Whichever decimal numbers you put, in whatever order, there exist some decimal numbers that are bound not to be included. We can spot some missing numbers by deriving them from the highlighted numbers showing diagonally, with a systematic change. The decimal formed from the diagonal above, if no change is made, is 0.3451. That number may occur further down in the series for all we know. But suppose we make the following change, creating an extra number. Whenever we encounter a 3 in the diagonal, we replace it with 1, and whenever we encounter anything that is not a 3, we replace it with 3. Our sample extra number starts off, then, as 0.1333. We are guaranteed that the decimal being formed is not in the infinite series given, for we know that the missing number differs from the first row's number by having a 1 instead of a 3. It differs from the second row's number by having a 3 instead of a 4, and so on, infinitely so on, down the diagonal. We can create more such missing numbers by different replacements. The set of decimal numbers between 0 and 1 certainly has more numbers than the set of natural numbers, even though the natural numbers are infinite in number. Differently sized infinities seem highly paradoxical, but we should remember that we are talking of abstract entities and ways of comparing them. After all, in the realm of chess, the bishop moves only diagonally, yet that tells us nothing about bishops in life and nothing about how wooden pieces labeled bishops can be physically moved. Yes, infinity does have application to the world. It also has misapplications. Let us see, by returning to infinities that are the same size as the whole number series, 1, 2, 3. Here is Hilbert's Hotel, introduced by another brilliant German mathematician. This one is David Hilbert, whose ideas and questions set off considerable mathematical research throughout the 20th century. Hilbert's Hotel has an infinite number of rooms, numbered 1, 2, 3. Every room is occupied. Yes, every room is occupied. No room is vacant. A traveler arrives. Paradoxically, he can still be accommodated, insist mathematicians of the infinite. Room 1 occupant is moved to room 2, room 2 occupant to room 3 and so on, for there is always a higher numbered room to move any occupant you care to mention. Room 1 is now available for the traveler. Even if an infinite number of travelers arrive, accommodation is no problem. Regarding the people already occupying the rooms, room 1 occupant moves to 2, room 2 occupant to 4, room 3 occupant to 6, room 4 occupant to 8, room 5 occupant to 10, and so forth. Thus, the infinite number of even-numbered rooms sweeps up all the established occupants, leaving the infinite number of odd-numbered rooms free for the infinite number of travelers. It is, though, baffling to describe a hotel with all rooms occupied, with every room filled, yet which takes new guests. With the infinite, every, all, and size need to be understood differently from normal. As for making sense of an infinite hotel, imagine meeting a weary Charlotte, walking the last few yards of a mile-long race. She started 1,760 yards away, and is panting the final yards, 3, 2, 1. That is fine, but it would surely be nonsense to think of Charlotte, or anyone as having started an infinite number of yards away, now sighing out the final 3, 2, 1. It is not a mere medical limitation that we cannot finish walking an infinite number of yards. It is not a mere architectural and material difficulty that prevents our building Hilbert's Hotel. And arguably it is not all that surprising that abstract infinite series generate paradoxes if applied to the world of hotel rooms, maids a milking and lords a leaping.